Okay, go ahead, Andrey.
Okay. Uh, so I want to introduce you deep equilibrium models, but I will start not from the description of this type of models, but uh, from the description of simple example of neural networks. So this this is So simple neural network with layers can be described in this way. So we have an initial input. We have some activation function. We have biases and with. This is the simplest way to describe neural network. Uh, so. Typically, how the neural networks works, we have a lot of layers, and we have information that's flow through all layers, and we have forward function and backward function. Uh, so the main idea of the deep equilibrium models that's we can as you can see, we can represent output of our neural network with some equation. And moreover, if one moment, please. We can represent our neural network with some equation, and the output of infinite infinite layers neural networks as a equation to fixed point. So let's describe our neural network as some functions with parameters. Sorry for index and so on. We can describe simple neural networks as a number of functions with some parameters that represent waves. The value from the previous layer and some input values. What we expect from this from all types of neural networks, of course. That's after some iteration, we will get the point when each new iteration that's not changing after additional iteration. after after apply additional iteration. So this is a stationary point of this equation. Of fixed points. That's mean we have the same value from the left and inside the neural network. This value not change anymore. And if we introduce some assumptions about the structure of this neural network, like that's all weights in neural network the same. This assumption can be explain why we can play the same waves for all layers and nothing changes. Nothing will change after this. So after this assumption, we can define all infinite layer neural networks as some function with parameters and some equation for stationary point. So the idea of these articles is that we cannot maybe it will be better not just iterate over each layer, but just solve this equation with some black box systems for simulation such equations. But so if we can formulate a full infinity depth Newton network as some function, and we can solve the stationary point, that stationary point will be our goal. That's what we can. That what we want to get from our neural network. But there is some problems. The main problems that's if we have some. Sorry, one moment. If we have some solutions that's represented by some um,
Hi, so just a quick question. So this
okay.
function f takes both z and x as inputs.
Yeah, that's I can describe. It
Okay.
takes the z and initial data, because if we just write this equation without any x inside it, and reformulate it as an equation, we will get an equation only on on fixed point, without any dependency from the input. That's strange. That's not what we want to get.
Well,
So
you will get dependence on the input because you set your initial state to be X. And so even if you, after iteration, get to a fixed point, if you start from different places, you may get to different fixed points.
Yeah, but in terms of equations, we will get just an equation for stationary point without any dependencies from the x. If we just rewrite
That's right,
this
but you will
equation,
have many solutions to the equations, and
yeah,
where you end up depends on where you start.
yeah, that's true. So the authors provides the idea that we can just input. We can take the input and insert this input in each layer. This is something like ResNet idea, but in terms of mathematics, which is we will get the equation that's depend from the x, not only z. Just an addition. This equation. Do you see it?
Yes.
Right.
Yeah, this equation represent the idea that we can add the initial value to each layer. So the main problem that's if we solve this equation with some default system for solution to this equation, black box root finding algorithms, we cannot backward through this stationary point. We just don't know how the root finding algorithm works. We're trying to create the system that will be worked without dependencies of the root finding system. So the authors provide the backward with theorems that can they provide the idea how we can calculate the parameters of these equations. So it's weights of neural network without our knowledge of root finding algorithm. This is simply just implicit differential. So they just take this loss function and just use chain rule and all this type of transformation to get the final equation in this form. This equation not depends from the root finding algorithm, but only from the Jacobian. Whereas G is just a f minus stationary point equals 0. So we can find the backward for our parameters in this way. And this is the main idea of this paper, that in fact, we just create the neural network represented by some simple functions. Function represents one block of neural network. So I can, maybe I'm speaking not too structured way, but F can represent not only one layer, but a block of neural network. You can remember that typically neural networks today works like some blocks that's repeating a lot of times. Blocks constructed from a different type of layers and activation functions. So F represents blocks. Not it can represent layers, but for neural networks that can get good predictions, can make good predictions, will be better to construct it like some type of blocks. So if we limit this equation into infinite, we will get the stationary point. So where virtually create the infinite layer neural network. There's this idea that can represent the infinite depth neural network. And we can solve it without any additional problem with memory. Moreover, these neural networks requires constant memory. This means this neural network is always one layer neural network.
So, Andrey, how is it different from unconstrained structure, where you are not thinking about this infinite number of layers, but just one network, and you just keep iterating it over and over again until you get to this point?
They look the same, but there is a lot of difference. In fact, in forwards and backwards.
I mean, what you're saying, that the backward pass you may be using the function that you calculate. That is different.
Yeah.
You can do it for any for any network. You can, instead of backpropagating, you can like do the estimation what the function really is. But the question is for the forward pass, there seems to be no difference from the unconstrained network.
For the forward pass, all that solution is just some root finding system for this equation. So there is no.
That's you're telling me how you're going to find the fixed point. But
a fixed point is
you're just replacing many forward passes with with finding a solution. But how is it different from what the unconstrained network does? Stefan, you're raising your hand, so maybe you have the answer.
Yeah, so it seems to me that unconstrained is a lot more general. Why? Because I think with unconstrained, with the right structure of connections, you can simulate any finite depth neural network.
Right.
You just have connections such that.
No, I know, but let's think about here this function that he writes, right? It depends on z and x to get x at next moment of time. So think about this f as just the entire network. Don't think about this as passage from one layer to another layer, but just think
there
about
is no
this.
Layers. There is no layers. In fact, there is just a function. So we just we are just implement the function. We don't.
I know this is just interpretation. You can interpret it as many layers, or you can interpret it as a function that takes some input state and shoots out output states. So I think if you're looking just on this function, equation 3, I mean, all it says there is some boundary neurons, input neurons X. There are bulk neurons. I call it Z, and then it gets Z at the next time step. And then it's up to you to decide how you're going to evaluate the fixed point. Are you just going to be iterating it, or are you going to be finding solutions and things like that? I think it's similar, but maybe there's something
that's similar in terms of we're trying to find the fixed points as in unconstrained networks, but the main idea is the learning process here, not just the construction of this model.
But the learning process will still be backpropagation, and again, depending on how you found the solutions, you will still have to backpropagate. You have to take a derivative of your function with respect to the trainable variables. I mean, you have to do it anyway.
Yeah, but this is only one iteration back propagation.
No,
so we I mean
no, it's not one. It's a chain rule. It's a hierarchy of backpropagation. It's not just one. So basically, what you have that f depends on the trainable parameters implicitly, explicitly, and also implicitly through the dependence of z's. And then you keep going backwards.
I mean, in classical neural networks, we need to backpropagate through all layers. There is no layers, so we don't need to propagate through
in
unconstrained
network. In unconstrained network, there are no layers. The same way.
In unconstrained network, we have a parameter that represents the number of layers time. So
you don't need this parameter. This parameter can be taken to infinity, and this parameter can be replaced with the tolerance, how close you get to the fixed point.
Okay. That's
so the number of layers there is not explicit, and also here, when you're going to do backpropagation, you will be doing the chain rule. You'll have to say how many steps backwards you have to take.
In fact, they said that this type of models represent all types of neural networks too. So I think that there is a deep dependency between the.
So I'm thinking they're the same. I'm thinking they're the same.
There are some requirements. One moment. Maybe,
so you still don't think it's the same?
Yeah.
Oh no, I think it's the same. I think it's the same.
I think
the same.
Yeah, I think
maybe there is some differences, but I'm not sure. So now it looks like this ideas the same, but in different terms. This is more this article is more focused on the idea how we can calculate the output.
Well, because AI can be like all of the hidden neurons, right? Like in unconstrained networks. So
that's right. That's what I'm saying. Each layer can be like all the hidden neurons, and then it's just the same thing.
I think that the idea may be the same, yeah. But as I said, the main focus on the backward part, when the authors provide the idea how we can backpropagate through fixed point without knowledge about root finding algorithm. That's my idea, I guess, but I'm not sure.
No, you can find the root, but finding the root is not enough. You have to differentiate the root around the root.
Yeah, and they provide the backward the idea how we can backward through this.
Okay, can you tell us how?
Root this equation, this backward, there is no root finding black box algorithms inside this equation. This is equation for parameters of neural network. There is no dependencies.
I'm not understanding this equation, so maybe you can explain it. You found the root, you found this fixed point. Now you're trying to determine how you can change the trainable variables so that the loss function is improved. What you have to do, you have to differentiate your network, the function that evaluates your network, with respect to the trainable parameters. Okay. Writing down as a Jacobian is not useful because we know it's a Jacobian. Finding that Jacobian is what the backpropagation is all about. It's always a Jacobian. It's always a change of the output variables.
There is some ideas how we can 1 moment. They state that we can just get the value of we can solve the root finding algorithm to get to the z with star, and we can just backpropagate through only one layer neural networks in terms of we write some equation that's represent the one layer or one.
Yeah, but that's not enough.
And
that's not enough. That doesn't tell you how the fixed point will change as a function of the trainable parameters. So this is only gonna affect the last step in the forward propagation. So what you really need to have is the chain rule going backwards, as we do in the unconstrained architecture. This is just one step backwards. You need to do infinitely many steps backwards.
I mean, they if you 1 moment.
So look at the equation 9. So there is a derivative of the function with respect to trainable parameters. Yeah. Okay, so this has equation 9, df d theta, right?
df d theta,
yeah. So that's only takes into account the dependencies of this f, explicit depends on f on theta. But then, of course, the z's also depends on theta. And then z's of the previous timestamp depend, and z's of the
1 moment.
So all of those.
This depends from the theta, of course.
Yeah, so it's not only f depends on theta, z's depend on theta, and then you have to backpropagate it to like, you know.
We can solve equation with 1 moment.
These equations you cannot solve. They are nonlinear equations, so there is no way you can solve it. But you can find derivative in the iterative fashion. Which this is exactly the backward pass.
They said that if there is some assumptions about the structure of if. That's mean if we can solve it for approximate this question, of course. I mean, the solve in terms of approximation.
Well, but then you can say like single backward pass, or not pass. Single backward step is an approximation, and then there is a 2-step backwards. That's a better approximation. There is a 3-step backwards. That's even better approximation. And of course, if you really want to understand,
of course, we need to iterate a lot of backwards to optimize the theta. Of course, that's true.
and only if you do that, you can claim your architecture is general. If you don't do that, then it's not general because it doesn't have
that's true. That's not what I'm trying to say. Yes, that's true. That's we need to optimize the theta a lot of times to get the result. Without it,
no, not a lot of times. For a single change of the trainable parameters, you have to take all the back propagation.
But there is no one moment.
It's not here. I don't see it, but it should be there. So this is only a single step back. You need to have infinitely many steps back. If you go infinitely many steps forward, then you have to go infinitely.
Why infinitely?
If you go in, well, of course, only a few steps are enough if it's a good fixed point and you converge to it fast, exponentially. But anyways, any forward pass that you do tells you that the state that you're going to get depends on the weights on each of those forward steps. Okay? And to get backwards, you need to go through each of those steps backwards. You want to rewind it.
They trying to replace these dependencies from the root finding system.
No, root find will just find you a point. It doesn't do the derivative. So you have to do the derivative.
So to get they calculate.
Now, what you can do, you can try to have a separate solver that will kind of function.
They try to separate the process of finding root and the process of training neural network. So
they're always separated. Those are two things are always separated. One is activation dynamics. Okay, and then once you got your fixed point, you wanna adjust your weights. That's a learning dynamics. Those processes are separated, but one depends on the other. They're coupled processes. They're not uncoupled.
Yeah, of course.
They're coupled processes, and so you cannot. So I think if they do take one step back, then there is a problem. Now I doubt that because well I don't know. So I doubt that they only take a single step back because that would be wrong. I'm sure they're taking more steps back, but then you have to somehow.
There is in one iteration there is one step back in terms of let me explain. This is a single update.
No, within a single update, within a single update of the trainable variables, you have to take infinitely many steps back if you are taking infinitely many forward steps.
I understand, but one moment, please. Idea that if we have we replace the infinite step forward with the root finding system. So we think that root finding system will be equivalent.
If it's easier to solve, of course, for large networks, it's harder to solve. So the question is it easier to find a fixed point solutions for nonlinear equation, or
this is a question.
Yeah, and it's usually easier to just iterate it.
So they make some experiments, and there is some assumptions about the differential structure of this.
So if you have a small system, I'm sure you can find a root by using some other methods. But if you don't have the root, and it's easy to just iterate.
They state that if we take the enoughly big set of parameters, we can will be equivalent as any other architecture. So the representation power will be the same. They stated this.
Look, let me just give you a simple example. A feed-forward network with the different layers, okay? When you take from input to the output, in the language of unconstrained network, is a fixed point, okay? And it only takes you as many steps as there are layers. Okay, now you can ask question, why not just find this fixed point by solving an equation? Because it would be very difficult. You'll have many more parameters, and for at least few layers feed-forward networks, it's easier to just, put it in and get the answer. And that will be a fixed point, by the way. But solving finding roots is not going to be nearly as fast, because for finding roots you have to use some other.
They said that there is assumptions about the neural networks is good enough to F is good enough to.
It's not about F. It's about W that I'm saying. So if W is a nilpotent matrix, okay, of rank 3, then it takes you 3 iterations to get to a fixed point. Okay, and solving, and you can have many parameters, but finding roots for such a system would be a difficult task. Now, taking only 3 steps forwards.
I can show you this. They explain this idea how that can be each neuron that can be represented as deep equilibrium network.
No, I agree with this. I agree that every network would be represented. It's. I think this is just identical to what I call unconstrained network.
Yeah. Maybe I think that yes, they looks the same.
But look at this in W. Look at this exactly
in different terms.
Yeah. So it is exactly the unconstrained network. So there is no difference there. The only difference is that they seem to be claiming that sometimes it's better to find the root than. That's only sometimes, and that's true. And then the back propagations, I mean, there shouldn't be one step backwards, but should be many steps backwards. But other than that, I think this is very same idea, the same idea. And the weight matrix looks exactly how it does for the nilpotent matrix. So everything.
Yeah, that's in fact why I want to discuss about this paper, because it looks the same, but using the different ideas in some points. I mean,
I think this is just this is exactly the same. So there is no difference in the. Now, the some of their more general things that we discussed for the unconstrained network, some of the more general connections, like from the bulk to input, are not here. But you can also have that, and that would be even more general.
They not focused on the wave matrix. They ignore that. Just replace all dynamics with the implicit function.
Right.
They not define this function or define the wave, and so on.
Right. That's interesting. Okay.
And this neural network provides, in this paper, not the best, but good enough results. But I checked the checked other tasks, and it's outperform or other neural networks and in the field of spatial alignment. That's at least in this task. That's the best solution. That's all.
Good. All right. Are there any questions? Comments? Oh, we cannot see anything. Are you trying to show us something else because you're switching?
No. Do you see now this?
No, that's good. Do you know if there were any follow-ups of this work, or this is it? Have they applied to anything?
This there is some types of book, not a book, but site, just a website with more deep descriptions of this idea, and some articles still.
Sure. Okay.
Some people trying to create additional improvement of this network. So yes, so I can send you this.
Yeah, you can share in this chat for the journal.
Okay.
Okay. Well, thank you, Andrey. If there are no further questions, I think we'll resume the meetings in January. So, thanks everyone for coming.
Thank you.
Thank you.
Bye.
Thank you.